Okay, in the Lagrange polynomial, in interpolating polynomial, we saw that there was two very big drawback in fact for in implementation. The first one was that if we want to compute the interpolating polynomial for a huge number of nodal points, for example, you consider you have xi and yi, you have lots of nodal point. So it was very difficult to compute Li of x, for example, for I equal to 0, 1, 2, and n, if n is a great number. And the other one was that suppose that you have computed the, in fact, interpolating polynomial, Lagrange interpolating polynomial for example, 3 points, and you want to add one more point. Okay, one more points. In fact, suppose that you have something like this, for example, 1, 8, 2, 5, and 3 minus 1, or 4 minus 1. You computed a P2 of x, and suppose that you add, for example, 6 and 2 here, and now you want a P3 of x. In this case, all of the computation for computing P2 is useless. Okay, are useless, and you cannot use the older computation for the new polynomial. Okay, so now I want to introduce you a new technique that solves this problem. Before I start to Newton polynomial, you have to, in fact, familiar with the Newton interpolating polynomial, the idea of the Newton interpolating polynomial, and then I introduce you a new concept that we call it finite difference, and we use finite difference to computing something like this. Suppose that Pn is the nth degree polynomial that agree with f of x at the nodal point x0, y0, and xn, yn. In fact, we know that Pn of xi should be yi for some nodal points that I is equal to 0 to n, for n plus 1 nodal points. So we can write Pn of x as P0 plus a1 times x minus x0 plus a2 times x minus x0 times x minus x1, and we continue in the same way until we arrive to the final term that is an times x minus x0 times x minus x1 times x minus xn minus 1. You can see that in this polynomial, if you put, for example, x0 here, all of these terms will be 0, and just it remains a0. And in the same way, if you compute P of x1, you will get a0 plus a1 times x1 minus x0, and here, because you have computed a0 in the previous step, you can find a1 in the new step. Now, we have to compute all of these a0, a1 until an. If we can compute all of these coefficients, in fact, we have computed a polynomial that we call it Newton interpolating polynomial of n plus 1 nodal points x0, y0 until xn, yn. So this is the idea of the Newton interpolating polynomial. Now, Let me put x0 in the Newton polynomial and we compute a0. If you put x0 here, this term, and all the other terms will be 0, and just a0 should be Pn x0. That we know that Pn of x0 is equal to f of x0. You will see that later we show this one as f of x0, that x0 is in a bracket. Now let x be equal to x1. So Pn of x1, okay, Pn of x1 should be equal to f of x0. It will be a0 and we put it here, okay, plus a1 times x1 minus x0, and we want Pn of x1 be equal to f of x1. From this equation, if you compute a1 should be f of x1 minus f of x0 over x1 minus x0. And so on. We can compute for a2 exactly in the same way. I have some computation later on. You can see that the computation for a2 later. Okay, now I want to introduce you a new concept that we call it finite differences. We have finite differences from order 0, order 1, order 2, and order k. Okay, we define the finite element, the finite difference of order 0, or zeros divided difference. We call it f of xi equal to f of xi. In fact, we put just two bracket instead of parentheses. Okay. Now, for the first divided difference for 2 points, for example, f of xi and xi plus 1. I say that you put your hand here and you in fact hide xi. What do you see? You see just f of xi plus 1. So write f of xi plus 1 in the denominator of the fraction. And then you put your hand on the last item. The last item is xi plus 1. What do you see? Just f of xi. You put f of xi and put a minus here. And then put xi plus 1, the last one, minus xi, the first one, in the denominator. This is the first divided difference. You can generate this divided difference for every 2 points. Okay? Now, for the second divided difference, we write it in this form: f of xi plus 1, xi plus 2. I say again, put your hand on xi on the first element. What do you see? F of xi plus 1, xi plus 2. Write it here. Put your hand on the last term in the brackets. What do you see? F of xi and xi plus 1. Write it here. And put a minus here. And finally, you put the last term minus the first term. This one. In the exactly same way, you can define the case divided differences. Okay? How? I say again, put your hand on the first term. What do we see? F of xi plus 1 to xi plus k. Write it. And then put your hand on the last term. What do you see? F of xi to x of a plus k minus 1, and xi plus I plus k minus xi. This is the case divided difference. Okay. Now for the polynomial, you consider at x0 we have a0 equal to Pn x0, it's equal to f of x0. So I can write it as f of x0. Okay, for the x1, we had f of x0 plus a1 times x1 minus x0 equal to f of x1. And this will be f of x1 minus f of x0 over x1 minus x0. If we write this one to form f of x1 minus f of x0 as two zeros divided difference over x1 minus x0, we can write it as f of x0 and x1. Okay, and for a2 we had this one. Okay, we had this one. So let me compute a2. Let me compute a2. In fact, we claim that the ak should be f of x0, x1 to xk. Let me compute a2 and show you how it works. For a2, we know that a2 is equal to f of x2 minus f of x0 over x2 minus x0 times x2 minus x1 minus f of x1 minus f of x0 over x2 minus x1 times x1 minus x0. You consider the denominator as the multiplication of these three terms and multiply denominator of the first fraction by x1 minus x0 and minus this one. These are some very easy computation that you are familiar with it, with this kind of computation from high school. Okay, now multiply these two parentheses and these two parentheses. Okay, and if you do the computation, finally you can get something like this. In fact, f of x2 minus f of x1, okay, over this minus f of x1 minus f of x0 over this, and you can write it to form f of x1 x2 over x2 minus x0 minus f of x0 and x1 over x2 minus x0. And this is exactly the definition of the f of x0, x1 and x2. So a2 in fact is equal to this one. In the same way, if we continue, we can find out that for all the coefficient we will get ak equal to f of x0 to xk. Exactly something like this that we have written in the previous frame in here. Okay, now if you consider the Newton interpolating polynomial, you can write Pn of x into form f of x0 plus sum k equal to 1 to n times f of x0 to xk times m equal to 0 to k minus 1 x minus x m. Okay, if we extend the sigma, you will get f of x0 plus here put k equal to 1. Okay, so you will get f of x0 and x1 times x minus x0. And for the other one, other term k, if k be equal to 2, so you get f of x0, x1 and x2 times x minus x0 times x minus x1. And so on. You can continue in the same way for k equal to 3, equal to 4, and finally equal to n. This is the Newton interpolating polynomial. The shape of this polynomial is very complicated, but in fact and in implementation it's not very difficult to compute, and in fact it was very easy to compute. How can we compute it? I tell you, you can construct a finite difference table to this form. You consider the first column of the table as in fact, x0, x1, x2, x3, and so on. The second column should be f of x0, which in fact is the zeros divided difference. In fact, this term is in fact f0, f1, f2, and so on. But you consider it as f of x0, f of x1, and so on. Now, by the definition of the finite difference, if you consider f of x0, x1, it will be f of x1 minus f of x0 over x1 minus x0. This is the first divided difference for x1 and f of x1 and x2. It will be f of x2 minus f of x1, f of x2 minus f of x1 over x2 minus x1. The other one, f of x3 minus f of x2 over x3 minus x2, and so on. These are the first divided difference. For the second one, you subtract f of x1 and x2 minus f of x0 and x1 over x2 minus x0. And for this one minus this one over this one minus this one. For this one minus this one over this one minus this one. For this one minus this one over this one minus this one. And so on. From these two, you can get f of x0 to x3, okay? And from this one, you can get f x1 to x4, and from this one, you can get the other one, okay? And from these two, you can get the other one, and from this one, you can get the final one. Let me show you the divided difference for example, 4 points here. Consider we have xi, in fact, f of xi. Okay? Consider, for example, 2, 3, 1, or 1, 2, 3. No different. 1, 2, 4, 8, 5, minus 1. Okay? Here, the first should be 5 minus 8 minus 3 over 2 minus 1. So this one minus 3. Minus 1 minus 5 is equal to minus 6 over 2 is minus 3 again. Let me put something else here. No, it works, no problem. Minus 3, and this is the first divided difference. The second one should be minus 3 minus 3, and it will be 0. Okay? It's all. It's finished. Now, the important note is that how can we use, in fact, this table to compute the interpolating polynomial. I tell you, you have to consider, in fact, the header of each column. For example, this one at the header of the first column, this one at the header of the second column, this one at the header of third column, and so on. And here you can consider, for example, this one, and this one. Now, if you want to write the Newton interpolating polynomial, you can write Pn of x is equal to f of x0, the header of the first column, plus the header of the second column, x0, x1, times x minus x0, this one. And then f of x0, x1, x2 times x minus x0 times x minus x1, and we can continue in the same way. For example, x1, x2, x3 times x minus x0, x minus x1, x minus x2, and we can continue in the same way until we arrive to x0, xn, okay, times x minus x0 times x minus xn minus 1. This is the polynomial, the Newton polynomial for some nodal points in a table, and it works very, very good. Now, let me show you an example here. This is in fact the algorithm of the nodal point. Let me show you an example. Suppose that we have a table like this. For x equal to 1, we get f of x, this one. For x equal to 1.3, 1.6, 1.9, 2.2, we get these values. Okay? So, you can construct the table like this. Let me show you. You consider the first column. In fact, these will be xi, x0, x1, and so on. The first, in fact, the zeros divided difference is the values of f at these points, exactly these values. And for these two, 1, in fact, we get f of x0 and x1. We have to subtract, in fact, this one minus this one over this one minus this one. The value is this, okay? And the other one can be computed by two previous values in the previous column, okay? Now, from this one and this one, we can get this one. How? We can subtract this one minus this one over this one minus this one. We can get this one, and so on. We can continue in the exactly same way. Also, we have a header for the first, in fact, column here. Now, if I want to write the interpolating polynomial, I have to consider the polynomial exactly like this: Pn of x equal to 0.765197, okay, minus 0.837057 times x minus 1. This is x0, okay? And we can continue in the same way, and I use the header of each column as the coefficient of the, in fact, the terms that have some multiplication of monomial, in fact. Now, you can write exactly like this. And if you compute, if you, in fact, expand this multiplication of monomials and do some very simple computation, you can get finally the P4 of x, and it works and very easy. Now, let me show you a theorem, in fact, about the a fact about the divided difference, in fact, of some points. Suppose that f be continuous on a and b, and f has the derivative of order n, continuous on the interval a and b, and suppose that x0, x1, and xn are distinct number in the interval a and b. So there is a number of like c in the interval a and b such that f of x0, x1, and xn equal to the derivative, the nth derivative of f at c over n factorial. Now, If you want to prove this theorem, you have to define a function, call it g of x, to form f of x minus pn of x. We know that f of x and pn of x have a relation between each other, and we know that pn in fact interpolate f of x. So pn at each xi is equal to f at xi. Okay, so in fact pn g of x, in fact g of x has n plus 1 distinct 0 in the interval a and b. And by the generalized Rolled theorem, we can imply that there is a number c in the interval a and b, such that the nth derivative of g at c should be equal to 0. You can take derivative nth derivative from both sides. In fact, here should be equal to 0. In fact, we have written something like this: gn of xc equal to fn of xc minus pn of xc, pn n in fact, of xc. We know that this is equal to 0 by the generalized Rolled theorem, so the left hand side should be 0 and the right hand side is something like this. So since pn of x is a polynomial of degree n whose leading coefficient is f of x, we know that the Newton polynomial is something like this. The coefficient of pn is to this form. So the nth derivative of pn should be n factorial times f of x0, x1 to xn. You consider pn of x, the last term is equal to something, and finally it will be fx0 to xn times x minus x0 times x minus xn. If you take the nth derivative of this one, the derivative of xn should be n factorial times the coefficient of xn. So it will be exactly like this. This is true for all values of x. So if you consider f of x0 to xn here, you can get f of x0, in fact the divided difference of x0, x1 to xn is equal to nth derivative of f of c over n factorial, and it completes the proof of this theorem. This theorem can be used in some, in fact, theoretical problems when we want to prove something. Let me finish this lecture here, and please follow and subscribe my channel. And I want to ask you, please watch my videos online, and please don't download my videos. And if you want to download my videos from YouTube, please play every video at least 10 or 15 minutes, and after that you are free to download the video. Let my channel improve, and let me use my channel. Thank you very much, and wait for the next lecture.